Okay, everybody, hello. I'd like to get your attention. First, I want to thank everybody for being here. Thank you for gathering. Especially I'd like to thank Dr. Braun for coming from Georgia to come visit with us. Today we have something a little bit different than we normally do. You'll notice we have some cameras in the corner because we are live broadcasting this particular event. It will be posted afterwards, but you can also watch it live. And we have two ways in which you can interact for those who are in the remote audience and even those who are here. The first way is through Twitter. And to access the Twitter account, you do #UMCOE. And we have Valerie in the back. Valerie, can you raise your hand? She's accepting all the Twitter feeds for us. And then the second way to access or provide some questions is through live stream chat. And the way to access the live stream chat is through the coe.miami.edu website. You go to the bottom right on media, and there's a click for the live stream chat. And we have Jaysha, who's accepting all the questions for the live stream chat. So at this point, I'd like to hand it over to Dr. Karkanian, who will introduce Dr. Braun.
Okay, thank you. Welcome, everyone. Thanks for coming. It's my pleasure to introduce Dr. Robert Braun. He received his PhD from Stanford University. He worked at the NASA Langley Research Center for 14 years and was the NASA Chief Technologist from 2010 to 2011. He's currently the David and Andrew Lewis Professor of Space Technology at Georgia Tech. He's a member of the National Academy of Engineering, Editor-in-Chief of the AIAA Journal of Spacecraft and Rockets, Vice Chair of the NRC Space Studies Board, and the co-author or co-author of over 275 technical publications in the fields of atmospheric flight dynamics, planetary exploration, design optimization, and systems engineering. So please welcome Dr. Robert Braun.
I'll figure it out.
Yeah, that'll check right away.
Cool. All right. If I put it there, does that work? Does that sound good? All right. Hey, good afternoon, everybody. Thank you for having me here for this weekend. It's been nice, sunny, wonderful Miami climate. Actually, I've enjoyed it a great deal. My wife and I came down this weekend, and you know, even in the rain, Miami's it's a great place. Actually, it's a very diverse city, much to see, much to do. What I want to do today, though, is talk to you about my research activity and my engagement in a variety of engineering systems. I sometimes have a difficult time explaining what I do to folks. The easiest way for me to explain what I do is that I land things on other planets. And what I hope to do today is explain to you some of the challenges about landing things on other planets, in particular Mars. Talk to you, I'm sure you all know that we've been successful at landing spacecraft on Mars. I'm going to talk to you a little bit about those successes, but then I want to pivot and talk about some of the challenges ahead for future missions. Let's see if I can make this work. There we go. So this is a slide that discusses the world's Mars program. And of course, we're sitting here in this room today with full knowledge that there is a Mars program, and that's a fantastic thing. I was talking earlier today, and I mentioned that when I graduated from Penn State in the late 80s, there was no Mars program. I was a guy who wanted to work on Mars missions, and there was no place for me to go. But that is certainly no longer true. At Mars today, we have a flotilla of spacecraft. We have orbiters and landers operating on the surface for a long period of time. Many of those missions are US missions. Some are European missions. There's soon to be some new partnerships with other countries. Of course, the Indians have an orbiter at Mars, and other countries are sending probes to Mars. But if you look at this slide here, you can see that we have orbiters that have been operational for the past decade. We have actually the Opportunity rover and the Curiosity Mars Science Laboratory rover that are trundling across the Mars surface today. And as they do, we're learning more and more about Mars, its environment for past life. And when we learn those things, we actually learn a great deal about life here on the Earth, how life on the Earth began, and where life on the Earth may be headed. So I personally believe that sending spacecraft out into the solar system and learning about other worlds is a good investment of our federal tax dollars. If you look forward into the future, you can see that the Europeans are about to send another orbiter to Mars. We are in the final preparations, hopefully, of sending the InSight lander, which will be launching in early 2016. This is a propulsive lander that's going to land on Mars. And what I spend a lot of my time on these days, I'm going to skip over the European rover. What I'm spending a lot of my time on these days is getting ready to send the Mars 2020 science rover to Mars. In 2020, we will effectively begin the Mars Sample Return Campaign, which is, for science-oriented people, is the holy grail of planetary science. We're going to go to Mars. We're going to scientifically gather just the right samples to tell us about past life on Mars. And then we're going to return those samples to the Earth, where we have rooms full of instrumentation to do detailed scientific measurement of those samples. There's never before been for the U.S., there's never before been a round trip, should I get that? Yeah. There's never before been a round trip mission like this that the U.S. has undertaken. So I'm very excited about the 2020 science rover. If you take a look at the science rover for 2020, you can tell it looks a lot like Curiosity, right? The rovers are about the same size. They have different instrumentation needs. They have different roving needs. They'll go most likely to different locations for those reasons. But if you look at the two rovers, from where you're sitting, they probably look fairly similar. So I'm going to spend a little bit of time talking about Curiosity. And I imagine that most of you remember where you were on August 5th, 2012, when we landed the Curiosity rover on the Mars surface. Whether you're in the United States, whether you were somewhere else in the world, how could you not know where you were, right? Do you know where you were on this night? Raise your hand if you do. Oh, come on, only a couple of you? Come on, you guys are being shy. Well, I know exactly where I was. So I and a group of people like me spent many years preparing this rover for its landing event on August 5th. And during that landing event, we can basically break it out into these phases: entry, descent, that I have broken out into two phases here, and landing, right? And so I'm going to be using the phrase entry, descent, and landing to refer to how we land spacecraft on Mars, where there's a planetary atmosphere. At the top of the atmosphere, the spacecraft's going very fast, and we basically use atmospheric drag generated from that aeroshell shape, that blunt body shape, much like when you put your hand out the car window, right? You put your hand like this, you get a lot more drag than when you put your hand like this as you're traveling down the highway. That's atmospheric drag, and that takes out maybe the first 90 to 99% of the energy that we start with at the top of the atmosphere. But that atmospheric drag alone on that shape is not sufficient to slow us down like we do here on the Earth. A skydiver jumping out of an airplane at the top of the Mars atmosphere would hit the ground supersonically on Mars because the density's just too thin. The density at the ground on Mars is roughly the equivalent to what we have here on the Earth at 100,000 feet. Okay? So imagine that the surface of the Earth, if you will, we're at 100,000 feet. We basically have to slow down from low Earth orbit to zero by the time we reach an atmospheric equivalent density of 100,000 feet. We can't do that on Mars with that aeroshell, so what we do supersonically is we throw out a parachute. We throw out a supersonic parachute. And all Mars missions to date have done this. Around Mach 2, we deploy a disk gap band parachute, and that slows us further. And then depending what we take to the Mars surface, depending on the size of the rover and where the rover's going, this phase, the subsonic descent phase and the landing phase, look different from mission to mission. Think back to what they looked like on Spirit and Opportunity with the beach balls and the bouncing and the rolling to a stop as an example. Or the Phoenix mission that propulsively decelerated all the way down to the ground but landed at a relatively high speed. In the case of Curiosity, we were taking the largest payload to the Mars surface that we had ever attempted before. When I first started working in the Mars program, I helped land a rover on Mars called the Sojourner rover. It landed in 1997, and it was about this big. It was the size of a little baby. It had a mass of 11 kilograms. Well, Curiosity is the size of a small car. It's 900 kilograms. All right, so we need a very different approach to land Curiosity than to land a little baby of a device, the Sojourner rover, all those many years ago. And that different approach was to propulsively decelerate with the sky crane descent stage, and then as we got near the surface, lower the rover, basically on a bridle, down to the Mars surface, where the rover wheels themselves would be the first thing to touch the surface. So there is no landing stage. We have rover wheels. And that means we have to interact with the Mars surface at a very low velocity, as I'll show you in a moment. Because those are the same wheels we use to drive around, right? To do the entire science mission. Of course, we now have a device about the same size as the rover, hovering, or not really hovering, but descending on the rover. And so we have to cut that bridle, and the sky crane descent stage flies away and crashes. And that was the drama that unfolded on August 5th, 2012. And many of you may remember that drama. If you don't, go to YouTube and check out 7 Minutes of Terror. It was well documented. There were people all around the country at landing parties watching this event, kind of biting their nails, because hundreds of activities had to all go just right in a perfectly timed and choreographed autonomous sequence to make this thing happen. And of course, as you know, on August 5th, it did. Everything went just right. Right? So now, one way to explain to you how challenging it is to land something like Curiosity on the Mars surface is to take a look at what we had done prior to Curiosity. So prior to 2012, how good had the United States been at landing things on Mars? Well, we had been pretty good, actually. We had landed 6 times successfully. And those 6 locations are shown in this slide here, with these little plus signs indicating their landing spots, their landing locations of these past missions. This is shown on a topographic elevation map. So blue is low and red is high elevations on Mars. And as you can kind of feed off of my previous comment about the lack of atmospheric density, you can kind of guess why we're going to these low elevation sites on Mars. We can't slow down enough to get to the high elevation sites. In fact, another way to look at this topographic map is shown here on the right. This is elevation on the x-axis and the percent of surface area on the y-axis. And you can see that all of our prior landings were clustered at what you might think of as below sea level landings on Mars. We had never landed anything on Mars with a mass greater than about 590 kilograms. We had never landed at an elevation above minus 1.4 kilometers surface elevation. And all of our landings, all of our prior landings, were in these very large footprints. Footprints with major axes on the order of 100 kilometers. So we hadn't landed very precisely on Mars. By the way, all of our past systems kind of look the same, at least from a hypersonics perspective. They all use the same thermal protection system. They all use the same aeroshell shape, a 70-degree sphere cone, and they all use the same supersonic disk gap band parachute. Now, these innovations were developed in the late 60s. In the lead up to the Viking program to Mars. The Viking program sent 2 orbiters and 2 landers to Mars in 1976. The first US landings, robotic landings on another planet. And these technology investments were made in the decade leading up to Viking. They enabled us to do Viking successfully, and to be honest with you, these investments enabled us to do all these other missions since Viking. In other words, NASA hadn't continued to invest in Mars landing technology. We were basically living off our past investments in this area. Now, you can do that for a while, right? And in fact, NASA had. So we went from a rover about this size, Sojourner rover that I mentioned earlier, that's my little baby there, to the Spirit and Opportunity rovers, all the way up to the Curiosity rover, which, as I've already told you, Mars 2020 is about the same size as the Curiosity rover. So you can think about how are we doing in our exploration of Mars? You can measure that a lot of ways. One way to measure that would be in terms of how much mass are we landing? How big are these systems? How capable are the systems that we're landing on Mars? And you can see in that axis, we're doing pretty well. We went from 25 kilograms all the way up to 900 kilograms, right? So we're up to the size of a small car. Okay. From a touchdown velocity perspective, I'll show you a plot in a minute to show you how we're doing on that, and I'm also going to touch on landed accuracy. But I want you to realize is that in doing all of these missions through the 90s to the present day, we have basically been living off of our Viking era technology investments. So here's a plot of velocity indicating for you how well we've done in terms of touchdown velocity. So this is the velocity that you have vertically and horizontally when we first interact with the surface. So imagine that you're the person responsible for designing the landing gear on whatever device we're sending to Mars. This is an engineering parameter that's probably very important to you to size that structure, right? What's the impact speed? What's the impact angle, right? Up here high, at this point here, it's all vertical velocity, no horizontal velocity. Over here, it's all horizontal velocity and shear forces and no vertical velocity. And what I've done on here is plot for you all the past missions, with one exception. No mission actually did this. This was actually the original design, is a kind of a historical artifact for you. This was the original design for Mars Pathfinder. When we did Mars Pathfinder, by the way, it took about four years for that mission to be developed at a total cost of about $250 million, which, is a pretty small amount, actually, for a space mission. And our approach on Mars Pathfinder is we were going to have 3 systems for entry, descent, and landing. Very simple, very elegant, I would say, approach. We had the aeroshell for entry, we had the supersonic parachute for descent, and we had the airbags for landing. There was only one problem. We couldn't make the airbags strong enough. So the problem with this system, once again, is the density on Mars is so low that we would hit the Mars surface with a velocity of, I don't know, 25, 27, 28 meters per second vertical velocity. And for the mass that we were carrying at that time, which was pretty small compared to what we're talking about now, we could never design our airbags strong enough to take that impact velocity. So what we had to do on Mars Pathfinder is we had to include rockets in our system. And so the way Mars Pathfinder worked is we had the parachute for supersonic descent, then we fired retro rockets to take out more energy, and then the airbags took care of the rest. And so the retro rockets took us down from roughly 28 meters per second down to something like 14 meters per second in vertical velocity. We then had an airbag design that was closed. Okay? So for Mars Pathfinder, we landed in this space. For the Mars exploration rovers, Spirit and Opportunity, we were taking more mass to the surface, roughly double the mass of what we took on Mars Pathfinder, in the same system, in the same set of airbags. So what did we have to do? We had to shrink the horizontal velocity. We couldn't tolerate horizontal velocities out here because we had too much mass. We were going to rip through our airbags in shear and tear those airbags apart. So we added this system, tiers and dimes, which was basically another set of solid rocket motors, to take out not just the vertical velocity, but also to reduce the horizontal velocity. And this is the way Spirit and Opportunity got to the surface. When we started to work on Skycrane, when we started to work on Curiosity, we realized right away we had a 900 kilogram beast to bring to zero velocity on the Mars surface. And we actually had designs that were airbag designs, but there was no chance that they were ever going to work for the mass that we were taking to the Mars surface. So we had to figure out how to slow down all the way to here, all the way to about a 0.75 meter per second vertical velocity and a half a meter per second horizontal velocity. And that's what that Skycrane propulsive descent stage did for you. The reason you didn't have a Skycrane on the previous missions is we didn't need them, right? We could solve that problem with a passive mechanical approach. But for the mass of Curiosity, there was just no way of getting that done. So we had to go with an active system, radar controlled, a lot of multi-thruster descent down to the surface, where we actually use the wheels, as I said, to land that. Now this is another way of thinking about capability, right? think about the engineering capability that it takes to go from here, right? This was where I was talking about being simple and elegant and low cost, down here. The Curiosity mission cost about 10 times what Mars Pathfinder cost, roughly speaking. And the reason it costs that much more is largely due to the complexity that's required to land something that large on a surface where there are no runways, right? There are no flat floors like we have here. It's a bunch of rocks and slopes and craters and all kinds of things. And by the way, the scientists all want to go to those places. The scientists don't want to land in a room with a floor like this. They want to land where the science is interesting, right? Where there's crevices, where there's features that they can scan with their different instruments. And so you end up having to go to these kinds of landing velocities. Now, another way to look at our capability is in terms of the performance, the landed footprint itself. And what I've done for you here is magically plot all of the landing footprints of past missions all in one location. Now, in reality, they landed all over Mars in all different locations. This is Gale Crater, where Curiosity landed, where Curiosity landed and is roving today. Gale Crater is a fairly sizable crater on Mars with a mountain in the center. And what we wanted to do is land the Curiosity rover, land this small car, inside a crater right next to a mountain. The only way to do that is with a little bit of precision, right? So if you don't have any control over your flight and you have poor navigation because you don't really know where Mars is, you'd be in the Viking mentality back in the 1970s. And this was the Viking footprint, so big it doesn't even fit on this image. When we did Mars Pathfinder in the 1990s, we had better ephemeris for Mars. We had a better idea of where Mars was, but we didn't have any spacecraft currently orbiting Mars, and so this was our footprint. The difference between this and what Spirit and Opportunity saw was because we had orbiters at Mars and we were tracking those orbiters, so we had a much better idea of where Mars was in its orbit about the Sun. That enabled us to fly the Mars Exploration Rover missions into this footprint, about 150 kilometers in major axis. A great improvement over Pathfinder and Viking, but still not enough actually to land in Gale Crater. You can't place this 150 kilometer footprint across Gale Crater, even if you ignore the mountains and you claim that it's all safe, which it's certainly not all safe. And so when we flew Curiosity, the Mars Science Laboratory, for the first time on a planetary mission, we actually had to fly. We had to fly the vehicle like you fly an airplane. We had to use lift. All of these other missions before MSL, before Curiosity, were ballistic entries. They had drag to decelerate, but they didn't generate any lift. They flew a symmetric shape at 0 degrees angle of attack, producing no lift. On Curiosity, we flew a symmetric shape at angle of attack, generating a lift vector, and then the onboard system would orient that lift vector up, down, based on the accelerometer measurements it was reading, and it greatly reduced the footprint to the point that we were willing to risk sending a $2.5 billion rover to a place on Mars, to a crater on Mars with a mountain in the center, and do what I call precision landing. Now in the future, we can do even better than this, by the way. In the future, we can reduce our landed footprint not to something like 20 kilometers, but we can get it down to within 1 kilometer on the Mars surface. In fact, I tell you, we can land on a football field on the surface of Mars once we put our minds to it. And let me explain to you how we're going to do that real quick. This is a simulation this is actually 3 different simulations of landing on Mars. And the reason I like this slide is the different phases are color-coded for you here. So the blue is the entry phase, where we have the aeroshell doing the deceleration. Then this yellowish, greenish color is the parachute phase, where we're descending on the parachute. And then if we use propulsion, that's in the red at the very bottom. Right? And you can see how late it is in the game when we turn on the rockets. We're basically just over the surface when we light up those rockets. We're using a radar measurement to figure out our altitude at that point. So take a look at this. This is what we did on MSL. This is with lift, guiding through the hypersonic phase of the atmosphere, flying hypersonically like an airplane might fly here on the Earth. But at this transition point between the aeroshell and the parachute, it's not very clean, right? Some of them transition over here, some of them transition over here in terms of range. And so what we're doing on Mars 2020 is we're adding something called a range trigger. And a range trigger basically deploys your parachute in the allowable conditions, in the right Mach number and dynamic pressure, once it also meets some range requirements, right? And so you get this nice correlation. When you're low in altitude, you're gonna do the entry a little bit longer. When you're high in altitude, you're gonna end the entry a little bit quicker, so that the parachute phase takes all of these points and brings them together. That's how you go from being about plus or minus 10 kilometers from the target to being plus or minus 3 to 4 kilometers from the target. Then if you add a little bit of fuel, and by the way, we landed with about 400 kilograms of excess fuel on Mars, on Curiosity. If you add a little bit of fuel, you can actually, because you know where you are and you know where the ground is at this point, you have a radar that's functioning, you can actually fly terrain relative navigation, just like a cruise missile, to a target. And so you can go from 3 to 4 kilometers to something like a football field on Mars. And I believe, it's not totally sure that we're going to do this yet, but I believe we will do this in 2020. We will land with an accuracy of something like this, allowing us to land, by the way, right in the middle of some really cool science on Mars. So if you go to Mars and you're trying to figure out where to land, and there's a big process to do that, imagine finding a safe zone that's 20 kilometers in extent. It's much easier to find a safe zone that's 6 to 8 kilometers. And it's even easier to find one that's just 200 meters in extent, right? So this capability means a lot for the future of the program. So no doubt about it, Curiosity did a great service, not only in the science mission that it's doing, but from an engineering perspective, it greatly enhanced our capabilities. Almost every metric you look at, you'd think, wow, Curiosity, man, they really advanced the bar, right? They sent the largest mass system ever to Mars. They landed the largest payload on Mars. They flew the biggest aeroshell that's ever flown, by the way. Only Orion will be slightly bigger at some point. They flew the highest design heat rate environment. We actually had to change our heat shield material to Pica because of that heat rate. It's the first time that Pica's flown at Mars. We flew with lift and we did hypersonic aero maneuvering for the first time. We greatly increased the size of the parachute, and on and on and on and on. Every system on Curiosity was bigger and better than anything we had ever done before. But let me tell you, they were all evolutions of what we had done before. There was no totally new technology that allowed us to land Curiosity. And I've done a lot of studies of this, and I'm going to show you these studies today. And my hypothesis is that MSL has taken the Viking era technology, the technologies that were invented in the late 60s, leading up to the Viking program, about as far as we can go. And, for 2020, for the Mars 2020 mission, that's okay, because we're going to land something similar to Curiosity. But what about for a mission like this? What about for my friend Mark Watley? He's on Mars. How did he get there? He got there in a system that looks like this. It looks nothing like the systems that we use today to land Curiosity, or that we used in the past to land Mars Exploration Rover, or Pathfinder, even Phoenix, right? And I think that the movie's got it right. The systems that we will use to land large payloads, and by large payloads, I mean, 5-ton payloads, 10, 20-ton payloads. Instead of a small car, frankly, I mean a 2-story house, right? The systems that we will use to land a 2-story house on Mars have very little in common with the way we have been landing what will be considered small robotic payloads today, right? And so basically what I'm getting at is we landed roughly a 1 metric ton system, 900 kilograms, a 1 metric ton small car on Mars. But for human explorations, we need to land this 2-story house right next to this other 2-story house that was landed autonomously, powered up, made the fuel, made the environment for the astronauts to live. Right? How do we land something this big? If you go look in any NASA study, they talk about landing 20 tons, 80 tons of payload, and they show these little cartoons, right? And they have the entry vehicle coming down, and then there it is. It's on the Mars surface. And they don't quite explain how it goes from being an entry vehicle flying this way to being a 2-story house on the Mars surface with this SUV out in front of it, right? Well, think about it for a minute. This system does not exist on Mars. I put it here just as a Photoshop trick. I put it on there. But that is the largest human spaceflight qualified system ever to fly. That's the Lunar Excursion Module. Went to the moon, right? We took humans to the moon. Look at the size of the Lunar Excursion Module next to my Mars houses. That gives you a good feel for the challenge that I'm talking about here. Okay? It's going to be tough. And what makes it tough, actually, is the Mars atmosphere. The Mars atmosphere is not really your friend in this regard. It's helpful, don't get me wrong. I'm glad there is a Mars atmosphere. We use the drag from the atmosphere to great lengths. But the problem with the Mars atmosphere is there's just not enough of it. So here's a comparison, altitude versus velocity, because I'm going to show you some trajectories in a minute. And what I'm basically showing you are different regions on the Earth. This is the Earth up above, and this is Mars down below. And these are the qualification regions of different flight systems that we use today on Mars. So if we're going to deploy a supersonic disk gap band parachute on Mars, it's been proven that if we throw that parachute out in this regime, in other words, at this Mach number and dynamic pressure, it will function as expected. If we throw that parachute out too early or at too high of a dynamic pressure, that parachute has been shown it will have problems, and we don't want to do that, right? So if I take this qualification box and I take it to Mars, it changes in shape and it changes in location. It changes in altitude, right? So the Earth is a great place. When we return to the Earth, let's say from interplanetary space, we're coming back at high speed. We typically throw out a supersonic drogue chute. We do that at about 40 kilometers altitude on the Earth. Then we decelerate over here and we throw out a subsonic chute. And then we just kind of gracefully come down. We're just enjoying our time, having a great time coming down to the Mars surface. We use sensors to find the ground. We maneuver. Time is on your side at the Earth. At Mars, when you do these things, look how close you are to the surface. You might be, when that parachute deploys, when you're going supersonically and that parachute deploys, you might only be 5 kilometers above the ground. And you're traveling at supersonic speeds. So you have very little time to do all the events that I just said Curiosity did successfully, those hundreds of events that all have to happen in a well-choreographed autonomous sequence. You have to do them in rapid succession at Mars, much faster than you have to do them at Earth, and that creates risk. And program managers don't like risk. So let me explain to you in a little more detail what I'm getting at. This is Mars. This is altitude versus velocity yet again. So you're starting way over here by the door, let's say, and you decelerate at high speed and you come down to this curve. This is Mach 3 right here. So you're traveling supersonically. And this is actually Mars Exploration Rover trajectory. So it's coming in, and the Mars Exploration Rovers went right in the middle of that box, this qualified box, opened up the supersonic parachute, and then they came over here. If we had carried a subsonic parachute, which we didn't for reliability reasons, we could have deployed that as well, and then we come down. We use the same chute for Mars for supersonic and subsonic descent all the way down here. And once again, if we had failed for whatever reason to deploy our supersonic parachute, we'd come down here and we'd hit the ground at very close to Mach 1. Okay? Now, as we try to stuff more and more mass into our aeroshell, and we need to do that. Aeroshells can only get so big, right? Because launch vehicle shrouds can only be so big. And the aeroshell has to fit in the launch vehicle shroud, right? It's a big origami kind of setup, right? So as we stuff more and more mass into our aeroshell, where we hit this parachute deployment box varies. And so what I have on this plot are all the past missions, Viking all the way through Curiosity. And what you can see here is they all decelerate hypersonically. They go through peak heating and peak deceleration with the aeroshell, and they all go into this box. And they all deploy a supersonic parachute and then come down from there. And then very close to the surface, we turn on propulsion and do whatever we're going to do, whether we have airbags or a sky crane descent. We do it in the last kilometer, and we come down to the surface. Okay? That's the way we've always done it. Well, look what happens as we stuff more and more payload, more and more mass into the aeroshell. There's a parameter called ballistic coefficient, and ballistic coefficient is basically a ratio of inertial forces to drag forces. So it's mass divided by drag area, okay? And if your area is fixed and your drag coefficient is roughly fixed because you're traveling hypersonically, the only thing that's varying in ballistic coefficient on all these plots is mass. So as mass goes up, ballistic coefficient increases and you go in this direction. Well, this curve right here at about a ballistic coefficient of 150 kilograms per meter squared was very close to Curiosity. If we had gone just a little bit more, we would have missed this box. We wouldn't have been able to use a supersonic parachute, and we would have had no way of landing Curiosity on Mars. And this is what I mean when I say that Curiosity took our existing technologies to the extreme limit of what they're currently qualified for. Another 100, 200 kilograms, and this thing is down here, and we missed the parachute box. Well, what's Mark Watley going to do now? He can't enter. Well, he can enter, but he can't slow down. He's got a big problem, right? And so when you see these cartoons, and you see companies and NASA and other people have these cartoons, they show these devices like this guy. This is called an ellipse sled. It's a very popular NASA concept. It's full of a human two-story house lander in there, right? They show them coming down, and then they show you that picture. But if you actually plot the trajectory, there's this gap. They miss this box. And sometimes they actually show parachutes on this thing, you know, decelerating them down to the surface nicely. But there's no way to actually do that. The physics just won't allow it. So there's this supersonic decelerator gap. And Rob Manning at JPL and myself identified the supersonic decelerator gap about 8 years ago. And we've been working ever since on ways to cross the decelerator gap. And the basic question that we've had, and largely this was from looking at those NASA cartoons, is how did the NASA guys go from flying in a shape like this, you know, almost horizontally across the Mars surface, to landing this two-story house in about 90 seconds, right? In fact, how did they go from Mach 5 to subsonic conditions? How did they discard that aeroshell? Where did it go? How did they translate over to the landing site? How did they take out all that velocity before hitting the ground? And what you have to remember is the ground at 100,000 feet density altitude on the Earth, right? So the ground is way up there in terms of what you and I think about every day, right? We're very familiar with our environment here on the Earth. And that's part of this challenge, right? So how do we get from flying to landing? Now there are many, so we actually published this, this hypothesis that there were going to be these challenges in a journal paper in 2007. And in that paper we put forward a number of options that might work, technology options that might allow us to cross that gap. And at Georgia Tech, since this paper was published, my research group has basically been systematically going through these options, both in the supersonic and the hypersonic phase. And I'm going to talk to you about a few of those here today, in the supersonic phase primarily. So this is some of the work that we've done at Georgia Tech in this area. It's all gauged at landing larger masses on Mars. Be that large robotic systems, that would be precursors to human exploration or human exploration themselves. And whether these are inflatable devices or deployable devices, whether it's the use of propulsion in a regime that it's not been utilized before, or new aerodynamic decelerators, the purpose of all of these technology solutions is just that, is to land larger masses on the Mars surface. And for a couple years at Georgia Tech, I was doing this work, and it seemed like, you know, to be honest, it seemed like nobody cared. And then lately, NASA has gotten very interested in this. And there are NASA people now pursuing these same things. There's a lot of NASA-funded activity pursuing these activities, and I'm going to show you some of the results of a couple of these new technologies. One of the technologies that I'm really thrilled with is the idea of a supersonic inflatable aerodynamic decelerator. Now, I'd like to say I invented this technology, but I did not. The supersonic inflatable aerodynamic decelerators, like all good things, were invented in the 1960s. They were actually looked at as part of the Viking, in that technology program that led up to the Viking missions. But when Viking picked a disc gap band parachute, people forgot about this, and they stopped working on this. And it wasn't really worked on again until the 2005 time frame when we started working on it at Georgia Tech. Now, the beauty of jumping from the late 1960s to 2005 is think about the advances that have been made in materials in that time. Once again, not by me, but by many, many others around the world. Materials technology has come such a long way. Now, the reason that I like this device, the supersonic inflatable aerodynamic decelerator, this is an image of one right here. This is it being inflated. This is it in its fully inflated state. This is that aeroshell, the 4.5 meter diameter aeroshell, and this is surrounding the aeroshell. So it's increasing the drag area, which allows us to take more mass to the surface without changing the ballistic coefficient. The reason I like this device is it's enclosed. It's relatively easy to analyze as opposed to a supersonic parachute that's flapping around in the wake of this device. And we can make them very strong, and we can ground-based test them. We can test them for strength in facilities, and we can even test them on the Earth at high altitude in Mars-relevant conditions. And so after we did some work on this device at Georgia Tech, this is a study that we did years ago at Georgia Tech that shows if we took Curiosity and all we did was swap out the supersonic parachute for this inflatable aerodynamic decelerator, that we could take 43% more mass to the Mars surface. That's a pretty big deal, right, for one change. And by the way, what can we use that mass for? We could use it for payload, obviously. We could also use it just to go to higher elevation sites that haven't been accessible to past missions, or we could add a bunch of fuel, and with terrain relative navigation, we could improve our landing precision. So this is a technology that I think opens up the door for a lot of the science instrumentation that we frankly just haven't been able to do. And the beauty of this is we were working on this in the university for a few years, and then NASA got involved in a big way, and they now have a project. It's called the Low Density Supersonic Decelerators Project. It's managed out of JPL. You may have heard of it. And they've actually been building and testing these devices at full scale. And it's, we couldn't do this at a university. It's the kind of thing you really need NASA or industry to do. It's on the cutting edge. And so what they've done is they've built 6 meter diameter supersonic inflatable aerodynamic decelerators. These things provide a 60% increase in drag over what we flew before. And they've demonstrated the required strength to operate them at Mach 4. Which means we can start the process earlier and gain back some of those timeline advantages that we need at Mars. So let me see if I can get this to work. So I have a little video that I might be able to get. I don't want to see the whole thing though, so I got to find that little bar. This isn't working. Yeah, you don't need to see this whole thing. It's a waste. All right, hang on. You can still see this. All right, so this is just a bunch of JPL stuff. All right, so one of the things that was cool is they're out in the desert. They have something called a rocket sled. And what we do in the rocket sled is we accelerate up to supersonic conditions on a track, basically a train track with rockets as the propulsive device. And then once we get to supersonic, we have a big aeroshell on the front of that train. There's the aeroshell. And then once we get to supersonic conditions, I realize the density is wrong, but we can inflate and take high performance video of the inflatable aerodynamic decelerator itself and see how it does. And those tests were done just a few years ago. Then with those tests in hand, the same team went out to Hawaii. And in Hawaii, they did a balloon launched. They basically launched a balloon that's carrying a rocket that was carrying this decelerator. So the balloon lifts them up to 100,000 feet or so. The rocket ignites to get you to Mach 4. And then the decelerator, in Mars-relevant conditions, inflates and slows the whole thing down. So here's the balloon going up. This isn't it. This is the spin up. That's the rocket acceleration. Let me get it to the right spot. That's the balloon going away. So hopefully you can see that. What's that? Okay, so here's the spin down, I think. That's what it should be. Oh, no, it's not. There you go. There's the spin down. And if you watch very closely, there's the limb of the Earth, right? From 100,000 feet on, it's beautiful footage, actually. There goes there it is, right? See how fast it happens? See how rigid it is? It's at Mach 4. It decelerated us down from Mach 4 into Mach 2 when they decided to test a parachute that I wish they hadn't tested. But they decided to test a parachute at Mach 2, and the parachute is probably what you've heard about. The parachute ripped itself to shreds. And I'll just, since we're here, I'll let you see that. But this is the parachute being thrown out at much lower speeds, much reduced forces. That's a volute, actually, that pulls the parachute out. I'll show you in just a second. The volute worked flawlessly also. Volute was a new technology, and there's the parachute. Oops. So, parachutes are not what you think they might be. Okay, so another technology that's of interest is called supersonic retropropulsion. It'll come back. Supersonic retropropulsion is I mentioned to you that we use propulsion in the subsonic regime now when we get very close to the surface. And so the idea was, well, why don't we just start using propulsion higher, at higher speeds? And the flaw in that has always been, aerodynamic instability issues, aeropropulsive interaction issues. No one had ever fired a real rocket engine into an opposing free stream at supersonic conditions. It had been discussed. There had been some studies done on this. And once again, we did a bunch of work on this at the university, showing that it would work at Georgia Tech. And then the coolest thing happened in 2013. It turns out that SpaceX was interested in this idea, supersonic retropropulsion, not because of Mars, but because they want to return their first stage. I think you probably know this. They want to return their first stage and make it reusable. Well, their first stage goes basically to space, right? So when they bring it down, they're actually bringing it down through Mars-relevant conditions. And to keep the first stage intact, they actually have to fire their engines at supersonic flight at about 100,000 feet on the Earth. So they fire their engines into an opposing supersonic free stream in Mars-relevant conditions. So I found out about this actually in late 2012 and started working with SpaceX on this. We brought some NASA people onto the project as well. And there was a NASA, Georgia Tech, SpaceX joint project to investigate this. It was, from SpaceX's perspective, it was 100% successful, at least in this portion of flight. They've now done this maneuver 7 times, all successfully. I'm not talking about the actual landing event itself. I'm talking about what happens at 100,000 feet. And from my perspective, it's been tremendously useful because we get all the data, right? We have all the data of what it's like to fire a real rocket engine into an opposing supersonic free stream in Mars-relevant conditions. And we've done reconstruction of those flights. So hopefully this will show you something. I might have to advance it myself. Here we go. So let me show you what that looks like. So here's the SpaceX. This is actually observed by a NASA aircraft. This is the SpaceX launch. This is the first. You see the first stage. You see the 2 bright lights. The bottom light is the first stage. The bright light above it is the second stage, continuing on to orbit. And what's happening is the first stage is actually maneuvering out of the wake of the second stage. This is all happening up high in space. The first stage is now maneuvered out of the second stage plume, is what those words say. And then the first stage does what's called a boost back maneuver. You'll see that in just a minute. The boost back maneuver is what they use to correct range. You know, they've gone down range and they want to come back for recovery. The boost back maneuver, it occurs at about 140 kilometers altitude. It has nothing to do with supersonic retropropulsion. It looks pretty. Other than that, I don't care. So they do the boost back maneuver. They do that flawlessly 7 times as well. And then as they're descending through the atmosphere, they go through what they call the reentry burn, and their reentry burn is supersonic retropropulsion. It's the first time, to my knowledge, it's the first time that this has ever been done with real flight hardware in Mars-relevant conditions. And you'll see that burn in just a minute. This was the subject of a couple of Aviation Week articles in 2013. It'll be unmistakable when that burn begins. It'll be right about now, or now. There you go. So there's the initiation of that burn at 70 kilometers altitude. You can see the turbulence associated with that burn. And this is powered flight, controlled powered flight through basically the same conditions on the Earth that we would experience descending a human system on Mars. So that data, to me, is priceless, actually. We got the data for a pretty good price, but it's priceless. So why is this important? It's important because those tests have direct relevance to where we're headed on Mars. SpaceX, as you may know, has been looking at something that they call Mars Dragon, looking at landing their Dragon capsule on Mars. The way they plan to do that is with supersonic retropropulsion, so with these techniques that I've been showing you. And meanwhile, NASA has picked up on that, and their cartoons have moved along, and they've gotten fairly detailed now. And so this is a concept that came out just this year for how you might send a crew of 2 or 4 to the Mars surface for maybe a week or a month at a time. And this concept uses supersonic retropropulsion. These are the supersonic retropropulsion engines. They would protrude through the heat shield in supersonic conditions. This concept is basically moving the SpaceX ideas that we've observed in flight forward to real systems. Now, there are other ways that you might land a large payload on Mars. I'm not going to go through all of them. Another way would be to just make our entry system bigger and bigger, right, so that we can take more and more mass without the ballistic coefficient going up. So you could imagine erecting or constructing or inflating a very large aeroshell in space after it's been launched. All of those things have complications with them. I don't think there are any showstoppers to any particular one of them. They all have pros and cons. But when you do that, when you erect a very large aeroshell in space, what it allows you to do is skip this supersonic qualification box, because these shapes tend to be stable through the hypersonic, supersonic, and subsonic regime. So you could take this shape all the way to the subsonic box and do whatever deployments or propulsion you're going to do down at the end with a shape like this. And NASA has a project now called the Hypersonic Inflatable Aerodynamic Decelerator that basically came out of this work. They've been doing ground-based testing, sounding rocket testing of these large inflatable devices with the idea of maybe improving the drag area so that we can take more mass to the surface that way. This result right here shows fluid structures interaction result, showing the deflected shape of the aeroshell in analysis versus experiment. You can see those lines are fairly close to each other, except out here at the end. So there's some evidence that one can construct a large construct and fly a large hypersonic shape this way. In fact, I don't have the video with me here, but they flew this sounding rocket flight, and this is a picture taken at Mach 6 of the hypersonic device here at the Earth in Mars-relevant conditions. So what I want you really to think about as I kind of wrap this up is how far we've come. Okay? So EDL technology readiness, at Mars, we can measure that a bunch of different ways. We can measure it in terms of how much mass we land on the surface, how accurate we can land, the velocities we have at touchdown, or how capable our future systems may be. In any of those axes, the entry, descent, and landing community in this country, and frankly in the world, has been making great strides over the last 5, 10, even 20 years. Are we on a path to send humans to Mars? You know, I think intellectually we are, but from a funding perspective, you know, a lot of these technologies are going to require flight tests. They're going to require a lot more funding than they're seeing today to make this happen. But there are some, you know, as opposed to 10 years ago, right? 10 years ago, if I was giving this talk, I would have said, I don't know how we're going to land humans on Mars. But today, I would say, I have some pretty good ideas. And it's not just me. Others have pretty good ideas of how we might do this. We need to just fund those ideas and do some fly-offs and see what makes sense. And we could probably figure it out. The really nice thing about this work is not only does it help us scientifically on Mars, you know, understand more about the solar system and the Earth, where we come from, where we're going, but these technologies are also useful for flight at the other planets. We can do Titan missions, Venus missions, what have you with these technologies. And there are both commercial and a broad range of exploration companies interested in these technologies as well. And with that, I'll stop and see if you have any questions. Thank you very much. Any questions? What do you think? Yeah. Sir?
We have a heating problem for the hypersonic deflatable stuff.
Yeah, so the hypersonic, one of the benefits of the hypersonic inflatable aerodynamic accelerators is they get such a low ballistic coefficient that they can decelerate up high. And so they actually somewhat mitigate the heating problem. They take the heat rate way down. Okay, and with advanced materials, you know, if you have there are a lot of materials out there that can take 10 watts per centimeter squared or 15 watts per centimeter squared. So the way we're dealing with that is we're going from 250 watts per centimeter squared on current systems that are rigid, making them big, taking the heat rate down to 10 or 20 watts per centimeter squared, and then we have advanced materials you know, that are designed to do that work, to take that.
Is that part tested already?
Some of it's being tested. There's a lot of work going on right now. There's arc jet testing taking place. Actually, that Mach 6 experiment, you know, encountered some pretty good heating. So there is work going on, but there's actually a lot more to be done there. Yeah. Yes, ma'am.
C. Newton asked, what is your favorite portion of the project to work on? Can you repeat the question?
Yeah, what is my favorite portion of the project to work on? I would say two things. So first of all, my favorite portions of the project are the early brainstorming. You know, when it's just a whiteboard and we're like, how are we going to do this? You know, and you're throwing out crazy ideas and you're, you know, no idea is actually too crazy. In fact, that's where the Sky Crane came from, actually. It came from a brainstorming session of about 15, 20 people who were gathered to kind of work on that problem. That's one of my favorite parts. And the other part would be really just the community of people that I'm privileged enough to work with around the country and around the world. There's several hundred people who are really focused on this and who spend their life's energy on this, and it's an honor to get to work with them. Those would be the two. Yes, sir.
So with your two-story buildings, is possibly already decided an optimum number for the human community and optimum time for the stage?
No, I would say that very little is decided about human exploration on Mars. I would say, though, that it just from conceptual studies, it's fairly clear that we're going to need to bring a lot of stuff with us, right? And it's not going to be, the systems are going to have to be much more capable than even what a small car can carry. Imagine driving across the country, right, from here to LA. Let's say we want to drive from Miami to LA. That doesn't sound that bad, driving across the country, right? So what's it, a few days or something like that? I'm sure some of you have done that. But what if I told you you had to bring all your own oxygen and fuel and food and, you know, habitat, and there was a radiation environment that you had to deal with, right? It gets pretty complicated quick, right? So fortunately, when you drive across the country, you stop and you eat at, you know, Wendy's or whatever. Whatever truck stop is your favorite. There's a hotel chain that you probably stay at, right? We don't have that at Mars, right? So we have to bring, certainly on the first missions, we're going to have to bring all that with us. And that's going to require something on the order of a 2-story house. That's what I was trying to say. Yes, sir?
What was the decision behind using solid rocket motors instead of liquid?
For Pathfinder and Mars exploration rovers, we use solid, repeat the question. What was the reason for selecting solid rocket motors on the early missions? The reason was it's basically a cost versus performance trade. So solid rocket motors are, lower, generally speaking at that time at least, were lower cost and less complex. We only needed a little bit of delta V, right? So we could get away with the lower specific impulse that those solid rocket motors had. And we needed rockets that we could trust, basically. Liquid systems are great, but sometimes they require pressurization, valves. You get into a lot of reliability issues. Is it going to be dual string? We got into all of that on Curiosity because there was much larger delta V we were dealing with, and the solids were no longer feasible, right? But if we're only looking to take out 15 meters per second, right, between the free fall without the solid rockets and the free fall with the solid rockets, it's kind of hard to beat a solid. Okay? Yes, sir.
Have you guys investigated utilizing the thermal energy during the reentry for slowing down, as well as also the linear momentum and maybe converting it to angular momentum? What kind of basic ideas have you guys explored?
Yeah, have you investigated using the, I'm repeating the question, have you investigated using the thermal energy in a positive way during the entry, descent, and landing process? So at Georgia Tech we have. NASA's not so interested in that yet, but I actually have a couple graduate students right now that are working on what you might call energy harvesting during the hypersonic phase. We're also looking at using the plasma to do control authority without lift. So there are a number of things that you can do in that regard. The problem with it, to be honest, it's a pretty short pulse, and so you need very large, what end up being massive systems to gather all that energy and store all that energy, because you only have a few minutes to do so. Okay. Well, in the back corner.
So regarding the navigation system, that the increase in precision that has developed over the past 60 years or so, at what point do you feel like it's basically just an INS system, correct, to land more accurately? Like it's all self-contained within the rover itself? At what point is there a lack of, is there a development of GPS or something using the orbiters that are?
Yeah, okay. Yeah, so the question is about navigation, how we navigate to Mars and what kind of precisions do we get with inertial navigation system, which is what we use today. So first of all, when I talk about terrain relative navigation, like in the future, then that is clearly breaking the inertial navigation approach. But it is true to say that to date, we have only done inertial navigation, right? And so the reason we had large footprints was because we had large errors, because we didn't know where Mars was, basically, that well in its orbit about the sun. And as we locked down on that source of error, other errors became the dominant driver, like atmospheric uncertainty or winds and what have you. And so those are the dominant uncertainties in our current abilities. So it's going to be hard to get below, let's say, 20 kilometers without doing something else. And the next thing we want to do is that range trigger. That's also an inertial device, right? So we can get down with the range trigger, we can get down to plus or minus a few kilometers, purely inertial. And then the next step after that, if you want to get better than a few kilometers, the next step is you have to find the ground and you have to navigate relative to the ground. Now, in terms of GPS, we don't have a GPS at Mars, and we're not going to have one anytime soon. But terrain relative navigation is, with onboard mapping, is basically GPS, right? If you have a map onboard the spacecraft, and you know where you are on the map, and you can look down and find features that tell you where you are relative to the terrain, then you can navigate very precisely. And that's how we're going to do that next step. Okay? One sec. Yes, sir?
What is the role of the previous missions during the landing? Are the robots communicating each other in any way?
No, so we don't use the landers to help. We don't use one lander to help the next lander because we actually don't expect them to be around that long. But we do use the orbiters.
I mean, maybe
No. So we use the orbiters. So we use the orbiters a great deal now. We use the orbiters for two things. So right now we use the orbiters because they send us signals and tell us where they are. So that's how we know where Mars is, right? And that helps us a great deal. And then secondly, when we do Mars science missions now, we don't send all the data back straight to Earth. Like on Mars Pathfinder, we had to design the missions, whole science return had to be a direct-to-Earth link, which is very power-intensive, low data rate kind of link. We do UHF relay to the orbiters now from the Mars surface, and the orbiters gather that data and then turn to the Earth later on and relay that data back to the Earth at a much higher rate. So we do use the orbiters today on Mars, but the landers are all kind of independent in a sense. There has been talk about, maybe sending a mission to Gale Crater in the future and having Curiosity cruise over afterwards and take a picture of it. But to be honest, it's just talk. Yeah. All right. Well, thank you all for your attention. I really appreciate it. Have a great day. Thank you, sir.
More duck kind of precision.
Oh, hey. Thank you. I appreciate it. Thank you very much.